Assalamualaikum everyone and welcome to my presentation. My name is Khairil bin HISHAMUDDin. My matric number is 210291. I am from section 442 and currently on the second semester of the engineering program at CFS IIUM. Today I will be presenting about one of the questions that my lecturer, Madam Siti MUNIRAH, assigned us to choose and explain in a video style presentation. The question I chose is question number 3. The question is about the Young's double-slit experiment, which involved the concept of wave interference. Without further ado, let's start by looking at the question itself. The question reads, a pair of narrow parallel slits separated by 0.240 mm is illuminated by green light, lambda equal to 546.1 nanometer. The interference pattern is observed on a screen 1 meter away from the plane of the parallel slits. A. Calculate the distance from the central maximum to the first bright region on either side of the central maximum. B. Calculate the distance between the first and second dark bands in the interference pattern. To grasp the situation in the question, we must first understand the geometry of the Young double-slit experiment. The following diagram shows a setup of the experiment. When answering the question about the experiment, we must pay attention to several values, which are lambda, the wavelength of the light, d, distance between the slits, l, distance between the slits and the screen, and m, the maximum or minimum order of the fringe. As you have probably noticed, the question orally provided us with 3 values for the setup, which are the values for d, l, and lambda. These values will be used in an equation in order to find y, the distance between center of the screen and the fringe. To answer this question, we must derive the interference equation which relates elements of the Young double-slit experiment together. Firstly, the path difference, which is denoted by the Greek letter delta, can be found from the yellow triangle in the diagram using basic trigonometry. From that, we get the equations delta equals to R2 minus R1 equals to d sine theta. Since L is much greater than d, the paths R1 and R2 are nearly parallel, so in the calculation, we just assume they are parallel as it is a very good approximation. Next, for a bright fringe produced by constructed interference, the path difference must be either 0 or some integral multiple of the wavelength. The equation we get from that is delta equals to d sine theta equals to m lambda. For a dark fringe produced by destructive interference, the delta is the odd number of half wavelengths, which is represented by the equation delta equals to d sine theta equals to m plus half times lambda. From the orange triangle, we can see that y divided by l is equal to tangent theta. Since the value as theta is very small, we can use the approximation tangent theta equals to sine theta. Finally, by combining the equations, we get the equation for the distance y for bright fringes and dark fringes. Part A of the question wants us to calculate the distance between the first bright fringe and the center. This means that we must use the bright fringe equation that we derived, and the value m is equal to 1. The calculation is as follows. After plugging in the values in the equation, we get the final answer 2.275 mm. Part B, on the other hand, wants us to calculate the distance between the first and the second dark fringe. Here, we must use the dark fringe equation and find the difference for m equals to 1 and m equals to 2. The calculation is as follows. The final answer for this part is also 2.275 mm. This answer is expected because the width of the fringes are constant throughout the pattern, and in both cases, A and B, the distance is between side-by-side fringes. That concludes my explanation for the Young's double-slit experiment question. Thank you so much for watching this video. Have a lovely rest of your day.